Okay, it's 1 minute past 6 p.m. I think we can start slowly. Some people might be joining also during the first couple of slides. So welcome everyone to today's webinar. We have a very interesting topic. Today we would like to talk about different faults in electrical machines and how to model them using ANSYS Maxwell. So I would start with set of rules, a couple of rules for the webinar. Please turn off your camera and turn off your sound. And if you have any question to our speaker, you can write it in our live chat. We have a live chat function, so you can raise a question there. And we will go through all the questions at the end of the webinar. And we also have prepared like a poll, like a question, a survey in the chat. You can also leave your vote there, and that help us to shape the webinar into one or another direction. We would like to know a little bit more about your experience using ANSYS Maxwell, about your technical knowledge about the topic, so we will feel ourselves more comfortable to frame it in a proper way. And I would start with a brief introduction about WiredWhite, about our platform, what we do and why we do it. So we envision ourselves as a network of engineers, as a platform that guides individuals, young engineers through their entire process of becoming, growing as an engineer, becoming an engineer. And we see our role in that matter as a sort of technology enabler by bringing customers and partners together, bringing students and partners, experienced engineers together using our platform, and we are providing the necessary tools for collaboration between them to achieve a smooth cooperation, to make sure that the problems are solved using our platform, the collaboration works smoothly, and so on. And why we do it? Because we would like to contribute to the acceleration and optimization of diffusion of electrification worldwide, meaning we believe that providing such a platform, such a EdTech, education technology platform, makes it possible to enable a global cooperation between experienced engineers, between our partners and less experienced engineers, students, and to support using our platform that cooperation that can also be global, and to support the knowledge sharing. And today's speaker is Ali Zent. I would like to introduce him today. So Ali holds a master's degree in electrical engineering. He has experience in machine design, electric machine design. He has studied in Tehran Polytechnic University, and he is a machine design expert with over 15 years of experience now, developing and consulting on the diverse electromechanic systems, on the electric machines, including gearless elevator motors, submersive water pumps, and wind turbine generators as well. And Ali has presented several professional workshops already on ANSYS, on Maxwell simulations, and on the topic of electrical motor design. And he has shared his practical insights, practical experiences into the electromagnetic analysis, into the optimization, and of course into the fault modeling and analysis. And his tutorials are very project-related, project-based. His lessons also project-based. And he helped already many engineers and students to enhance their practical understanding of finite element simulations, FEA analysis, and electrical machines. So welcome everyone, welcome dear attendees, and welcome Ali Jant, today's speaker. The floor is yours. Looking forward to the webinar.
Okay, thank you, Dimitri. And Hello everyone, I'm glad that I'm presenting this webinar about modeling different faults in electrical machines. Please confirm that you're able to see my presentation.
Yes, we can see it.
Perfect. Today we will talk about different faults in electrical machines, and it's a useful topic because if you are an electrical engineering student, it will help you to choose a good topic for your thesis. It has potential to publish papers on it about modeling faults, diagnostic of them, and the effects of fault on machine operation. And if you're an engineer in industries, it will help you to understand the behavior of machines under different faults, and it will reduce the risk of failure. It will reduce the maintenance cost and downtime of the machines and systems. Early detection will prevent the downtime of the machine. So we have to know what will happen when a machine has a fault, because usually these faults will be progressive and makes the situation worse. So we want to understand the behavior of machines before they failed completely. Let's have a look at the classifications of different faults. Most of them have overlap with each other, but in these categories we can see the electrical faults inside the stator or rotor winding, and we have supply faults like voltage sources faults or inverter faults. We have magnetic faults. Again, this eccentricity, demagnetization is completely magnetic fault, but eccentricity has overlap between magnetic and mechanical faults. In this webinar, in the live demo, we will focus on the eccentricity fault, how to model it, what is this fault, and what is the results of this fault in the motor operation. We have thermal fault, like the overheating, insulation degradation, and mechanical faults like bearings, shaft, and misalignments like eccentricity. If we want to talk about the stator winding faults, we have different scenarios in this fault, like turn-to-turn, or we call it inter-turn in the papers, turn-to-turn short circuit. As you can see here, we have loss in insulation, so some of the turns will have connected to each other, short-circuited. It will have some effects. In this machine, we have only one coil beside each tooth, but if we have different coils, we may have phase-to-phase short circuit, phase-to-phase fault, or phase-to-ground or housing fault. The root of this fault, all of them can be insulation aging or thermal stress that makes the insulation fail. Or voltage surge will create arcs between the windings, and it will make the insulation fail too. Mechanical vibration and friction, especially when we are assembling the winding, will happen a lot when we want to put the coils in the slots and we have a short slot opening. Usually this friction will damage the insulations of the winding. And chemical contamination and dust, oil and water can cause this fault too. What is the results of this fault? Of course, we have unbalanced phase currents because we have not balanced winding in three-phase. Localized heating, we will have hot spots when we have a short circuit coil. We will generate a lot of heat in a single point. and it will reduce the electromagnetic torque and risk of cascading failure. The fault will start at a single point, but it will be progressing and make the other insulations fail too. Before going to the next slide, Dimitri, can you confirm that still the voice and PowerPoint
Yes,
is okay? Okay.
All crystal clear, yeah.
Perfect. Thank you. We talked about the faults inside the stator. Let's have a look on the rotor's fault. I categorized them into broken rotor bars, end ring cracks, and field winding faults. Of course, the first two will only happen in induction machines with a squirrel cage rotor. It only happens in this kind of machine, but this special kind of machine is used more than 90% of the motors inside the industry. So it's very important to be able to diagnose this fault and know the effects. If we have a winding inside the rotor, we will have a possibility of open or short circuit field coils or insulation breakdowns. If the field coil and if the winding of the rotor has some problems, it will weaken the excitation and unstable operation point for the motor. About the broken bars and end ring cracks, we have almost the same effects. We will have more torque ripple, unbalanced field, localized heating on the crack or disconnected part, and the starting torque will decrease and the torque ripple will be increased. And we have more losses inside the machine. But the reasons of these faults sometimes have different causes. For example, in the rotor bars, we may have fatigueness or heating up and cooling down, thermal cycling that cause having a broken bar. We may have manufacturing defects in die casting. If we have very small slots inside the rotor, the possibility of not connecting the aluminum inside the bars is high. And when we have line start induction motors, the high in starting torque will or high starting current, both of them will cause shock inside the bars and make them broken. About the end rings, because usually in the motors that we have copper instead of aluminum, we have to connect the rotor bars together and weld them, and it may cause some problems in the joint quality, and we have stress and fatigueness to the end ring too. About the permanent magnet demagnetization, that is a very common fault inside motors with permanent magnets like BLDC or PMSMs. It means that we have partial or complete loss of magnetic resonance, the strength of the magnet inside the motor. Some causes we can count like high operating temperature near the Curie, or even when we have high temperature, even below the Curie point, still the demagnetization curve will be lower, and with lower negative magnetic field, the magnet can be demagnetized completely. We have high temperature problem here. If we have high temperature, the risk of demagnetization will be higher, and excessive armature reaction in fault or overlap. When we have negative flux density in the comparison with the magnet's flux density, we have the risk of demagnetization. And of course, mechanical shock and impact will damage the magnets too. It will reduce the torque density, it will reduce the efficiency, we will have higher current for creating the same torque, and we will have higher torque ripple and vibration inside the motor. And the fault that we will talk more in this webinar is the eccentricity. Eccentricity means unequal air gap between the stator and rotor. We have, with this definition, we have different eccentricity types: a static eccentricity, dynamic, and mixed eccentricity. The static eccentricity is happening when the rotor center and the stator center, both of them are fixed, but they are not aligned. They are not at the same point. We have a smaller air gap in some part and a bigger air gap in other part, but everything is fixed. The air gap is fixed in this position. And we have dynamic eccentricity when the rotor center rotates around the stator center. In this way, the air gap is not uniform, and the smallest part and biggest part will change in each cycle. And of course, we have a mixed eccentricity that is the combination of both of these faults. To have a better view, I created an exaggerated video about each of these eccentricity. As you can see, in the static eccentricity, the rotor center is fixed, the stator center is fixed. They are not just coincide, they are not at the same point. In the dynamic eccentricity, the rotor center will rotate. And in this way, we have not uniform air gap and it will change in all time steps. And with the mixed eccentricity, both of these faults are existing here. To review some causes of these faults, I gather some of them, but of course you will see the recorded video of this. You will have access to the recorded video and this PowerPoint if you fill the chat box and the poll that my colleague shared. The cause of static eccentricity usually refers to the manufacturing tolerances and bearing misalignment. Usually the static eccentricity happens inside the manufacturing process and it will be fixed. A stator core deformation will cause static eccentricity too, or rotor positioning during the assembly. And we sometimes we have some faults in the frame and the frame is distorted. The dynamic eccentricity usually happens when we have in the operation point, we can have bearing wear or looseness, rotor shaft bending or deformation. It can be due to the magnetic forces or thermal problems. Unbalanced rotor when we have uneven mass distribution on the rotor, and thermal expansion if we fix the both side bearing and we have a hot shaft, the thermal expansion will cause some deformation in the shaft. We have mechanical resonances that makes vibration and deformation of the parts, and magnetic unbalanced when we have asymmetric magnetization force because of the demagnetization or different magnets type. It can cause the dynamic eccentricity too. Okay, we have another type of faults too, external supply faults that have some different categories like the imbalanced voltage, We have some thresholds with the standards for this fault when the three-phase amplitude or angle between the three phases are not balanced. We have imbalanced voltage. We may have over voltage or under voltage due to the network or grid situation. This will cause some problems. We can simulate the motor under this fault and measure the effect of this fault on the operation. We have phase losses and harmonic distortion too when we have a lot of VFD or power electronic systems inside the grid. They force some harmonics inside the voltage, and these harmonics will increase the loss inside the core and will cause some problems like torque ripple. If we have a disconnected phase, on different motors, it has different effects, and we can simulate them and measure the changes. I summarized different faults here. We talked about them: winding short circuit, broken bar, bearing wear, eccentricity, demagnetization, and thermal fault. And for each of them, we mentioned some primary causes, key effects, and detection methods. Now we will go to have a live demo in the software to model the eccentricity fault. And after that, if you have any question, you can write during the webinar, or after that, you can write your questions inside the chat box, and I will be glad to answer them all. Please confirm that you can see the ANSYS Maxwell environment.
We can see it, Ali.
Okay, thank you very much. For simulating the project with a static and dynamic eccentricity, I choose a surface-mounted permanent magnet synchronous machine, a surface-mounted PMSM. You can draw the whole geometry by yourself manually, or you can use RMExpert models, the predefined parametric simulation, predefined template-based model of the motor. But just remember, to model the eccentricity, you need to have the whole model, the complete model of the motor. Because if you use the symmetrical boundaries or periodic boundaries, it will model the eccentricity or any other faults like demagnetization, coils, and other faults uniformly and periodic on different segments too. So you will not see any effect, or you will extract wrong results. So to model any faults, try to have the complete model of the geometry. I created this model with RMExpert. It's one of the default examples of RMExpert. But to have a better view and easier simulation, I made the air gap a little bigger. Now we have 1 millimeter air gap between the rotor and the stator. Now let's start to, this is the healthy machine. Everything is at the center. The rotor is at the center of the stator, and center of rotation is coincide with the stator. This is the healthy machine, and for getting the results, first model the healthy machine and extract all the results. We will see differences in the torque, in the back EMF, and in the current harmonics. I model this simulation as a healthy one. I will make a copy to be able to model a static eccentricity. Just copy the healthy machine to have exactly the same geometry and setting to be able to compare the results. I create another model and rename it as a static eccentricity. Static. We talked about static eccentricity. It will change the center of the rotation in comparison with the center of the stator. So now how can we model that problem? Remember, when we use a band, when we assign a band for the rotation, of course, we don't have enough time to review the modeling of the machines step by step from the beginning. But if you create your model from the RN expert, it will assign most of the parameters automatically. When we have a band of rotation and we assign it, we choose the moving vector around the global Z. We can define different coordinate systems, but for easier simulation, I choose this way. Don't change the rotor center. Always the rotor will rotates around the center of the global coordinate system, around the Z axis. So we don't change the rotor setting. Instead, we have to select all the other parts than the rotor, like all the coppers. I will select all the coppers, a stator, and remember to not forget about the outer region or any other parameters, any other parts that are related to the stator. Because if you move some of the parts and not move the others, we will have some contacts and overlaps, and you will have errors. So the center of rotation of the rotor is the global center. I want to change the center of a stator instead. It doesn't matter if we change the rotor or a stator. For a static eccentricity, the easiest way is to select all the parameters of the stator and move them. For example, we have 1 millimeter air gap. I want to model 30% eccentricity. So I will shift the whole geometry from 0, 0, 0 to 0.3 millimeter in the X direction. You can choose any other vector to model the eccentricity, but it doesn't actually matter because the motor is rotating and the results will be same. I made a mistake here. I have to retype the 0, 0 and enter. I think I again made big values. If you want to type exact value, use the keyboard to change the numbers. I use the mouse button and it makes a problem here. I have to do it again, select all the values, move it from 0, 0, 0 to 0.3 millimeter. It's a very small change, but that's the way that it happens in the real life too. We have we have half of the millimeter air gap, and with only 10% eccentricity, we will have very bad results from the output of the machine. Now you can see here, the rotor is more closer to the stator teeth, and in this part, we have bigger air gap. That's how we model the static eccentricity. Before moving on to the dynamic eccentricity, I want to let you know a trick that create a parametric simulation. Actually, the ANSYS Maxwell will not let you use the parameter in the moving part. When you are moving objects, you cannot put parameter inside the values of movement. But after you moved everything, you can right click on the name of the simulation, come here in the design properties. When we add the parameters, add a parameter like a static ECC, a static eccentricity. Choose the value as the length and millimeter and make the initial value as 0.3 millimeter as I designed. Now you have a parameter named static eccentricity. You cannot move everything when you're clicking on the move object. But in the design tree, you will see all the parts that are moved. You can select all the movements one by one, select all of them with holding the control button. After you selected all of them, come here in the properties. You will see all of them moved with the 0.3 millimeter. Instead, you can write your parameters that you created. In this way, I don't want to spend time for selecting all of them. I selected some of them, but I want to show you the effect. If I select the sum of coils, and let's do the same for the stator core 2, the static eccentricity. Click on apply. And in this way, without doing the same process again from the beginning, you can simulate different scenarios with different eccentricity sizes. Now I have a parameter here that I can make it. I want to do exaggerated geometry, like for example 10 millimeter. Of course, we will have intersection, but when you change this parameter, it will automatically change the geometry, so you don't need to do it again manually. I will show you another solved simulation about the static and dynamic eccentricity that shows this parametric simulation for different scenarios for different percentage of the fault. Okay, we talked about the static one. Let's have a look on dynamic eccentricity. For modeling the dynamic eccentricity, let's make the static one as a 0 to not have any intersect or confliction. In the dynamic fault, we have to move the rotor center inside the band. It's a very important point in the simulation of ANSYS Maxwell. It doesn't matter what shape is inside the band. It will rotate the whole geometry around the center of the band. So if you move the one magnet or all the magnet and rotor in the same direction, it will rotate all of them together inside the band. And the band should be at the center of the Z direction. You don't need to change the band, but you have to change anything inside the band as a rotor. And another point that is very helpful in your simulation is, especially when you want to model mixed eccentricity, when you create a static one and dynamic one together, you may have some intersection. Manage the band size to, for example, if you want to model a static eccentricity and move the whole stator, make the band closer to the rotor. And when you want to model dynamic eccentricity, make the band bigger to be closer to the stator. In this way, you can have better free places to move the rotor parts. Now I will go to the design tree, and increase the diameter of the gap for example, 75.5. Let's see if it's working or not. Yes, you can see the band is bigger now and it is more closer to the stator teeth. In this way, I have to select all the rotor parts like rotor steel, all the magnets, and again, don't forget the vacuum part. We have inner region inside the rotor that should be moved. Again, you have to click on move, select a center for movement as 0, 0, 0, and move the bodies to, for example, 70% of air gap. Let's see if we have any intersect or not. In this way, we will have asymmetric air gap and we didn't move the shaft. Yeah, don't forget to move everything inside the geometry, inside the band. Now we have again asymmetric air gap, as you can see, but it will rotate with the time, as we have mentioned here in this slide. The dynamic eccentricity will behave like the middle one. The whole rotor center will rotate around a circle. You can use the parametric simulation here too when you created the movement. After the movement, select all the move operation and change it to the name of a parameter. Now in the optimetrics, you can add a parametric simulation and sweep the static or dynamic eccentricity. Just pay attention to not have any intersect between the parts. You have to use the limits of your design. This is how we manually model the eccentricity. Static and dynamic and mixed eccentricity is a combination of them. In the newer version of ANSYS Maxwell, if you go to the ACT extension, you will see a wizard that you can use for modeling the eccentricity. If you open the wizard, you will see Maxwell eccentricity. Maxwell eccentricity. You can click on this wizard. It will help you to model this fault, but it will work perfectly when you created the model from the RM expert. If you changed any part, for example, change the shape of magnet, deleted the magnet and redraw the magnet by yourself, sometimes it will cause some problems. It will move all the magnets except the magnet that you draw, or except the parts that you added to the simulation. Sometimes it has errors, but the workflow is the same. It will do exactly the same as we talked. For rotational part eccentricity or rotational axis eccentricity, one of them will choose the rotational center and one of them will change the rotation, the misalignment between the centers of the rotor and stator. This is how we can use the wizard of eccentricity inside the Maxwell, but still I suggest you to do it manually to have the full control on the simulation that you are creating. And another point is we discussed about 2D simulation and the type of eccentricity, but we have another type too, that the rotor center at the bottom of the stator will change in comparison with at the end of the stator. But for this modeling, you need to create a 3D model or use some estimation for that. In other ways, you cannot model that inside the 2D simulation. And 3D simulation will need a lot of time and resources to be analyzed. Modeling all the faults. I mentioned that point that you need a complete model for the simulation, but modeling these faults on different machines will create different results. For example, if you have this 4-pole magnet and you have a demagnetization fault, for example, one of the magnets are weaker than other magnets or stronger than other magnets. When we have 4 poles with this stator winding, and we have a rotational rotor that has a fault like eccentricity or demagnetization. Sometimes this coil will compensate this coil's problem. So you will not see the result exactly. That's why you have to create plots from the torque, from the back EMF, from the flux density to find the problem inside the results. For showing the result of fault, I have a pre-solved simulation file. I choose the induction motor, a squirrel cage induction motor for this example, because these motors like PMSM have intrinsic torque ripple. So finding the additional torque ripple when we have fault is a little bit harder than induction motor. But applying the fault is easier for this example because we have lower number of elements. So for applying the fault, I use this simpler model, but I applied both faults on this motor before and analyze the simulation to have results to discuss. Now, first, let's have a look on the static one. For static eccentricity, I modeled this move parameter to move the geometry, to move the stator and all the coils. And I solved, let's have a check. I solved the parametric simulation in 3 different steps. 30% eccentricity and 60%. The same happened for dynamic one, 2 different values and the healthy one. If we use the 0 movement, 0 displacement, it is the healthy machine. And if we use the other parts, we will have faults inside the motor. So let's check the results. We have 2 kinds of results that we can use for finding the eccentricity problem. First is the field reports, like plotting the magnetic flux density or flux lines to see if it is symmetrical or not. Come here in the field. The best way is to use the magnetic flux density, magnitude of the B, and click on OK. It will plot the flux distribution in the selected time step. You can use this plot to find out the problem, or you can draw some lines inside the air gap. But remember, if you want to use these plots, you have to save field inside the analysis setup. Be sure about it that you selected enough points for saving field. In this simulation, we don't have any problem. We don't have any eccentricity. We have 0 displacement. So you can see the field report is symmetrical. Everything is symmetric around the global Z. But let's have a look on this other simulation that I plotted the field. you will see the distortion in the flux density. What is the problem of this? When we have distorted flux density, in some parts you will have saturation, in some parts you will have lower flux density. But in the parts that you have higher flux density, we will have hot spot, the core loss will be increased, and even the magnetic forces will be changed, and this fault will cause, and it will be the first step to other faults too. We can plot different parameters in the field, like the loss distribution, field intensity, current density, and other stuff. It depends on your simulation. For example, in this induction motor, we can plot the current density inside the rotor bars to see if the eccentricity changed the distribution of the current or not. You can plot all of them together in the results. Let's have a look to use our time more efficiently. Let's have a look on the other results too. First, let's plot the torque of this motor when we don't have any problem. You can see I choose this induction motor because it has a very, very smooth torque when it reaches to a steady state. But to plot the other values of the fault, I have to come here to the plot properties, go to the family, and change and choose other values of the misalignment too. Now I want to plot 0% eccentricity and 30%. If I apply the diagram, you will see both diagrams, one without any torque ripple and one with higher torque ripple. If I zoom in, you will see the torque ripple has its own frequency too. And this frequency is one of the main points that we can diagnose the problem. Let's have a look on the other fault, 60% fault too. In this way, in this fault, you can see the torque ripple is much higher. The average torque does not change at all, but the torque ripple increased a lot. This will happen in the other parameters like current too. Let's just plot the phase A with different eccentricity levels. Phase A with all values of the fault. One of them, the first current without the fault, is purely sinusoidal. But when we have eccentricity, you can see different harmonics will be added to the simulation. An important point is to create FFT, Fourier transformation, from this current to be able to diagnose the fault. That's the way that we use for diagnosis in real industries too. They measure the current, they extract the harmonics of the current, and they can understand there is some fault. And related to the frequency of those harmonics, even they can estimate the severity or the type of that fault. For creating FFT, I want to mention this point too. You need to plot the diagram after the steady state. Don't plot in the initial and transient part. So I will choose for example, plot the diagram between between 300 millisecond and 400 millisecond. I will add the new plot. When you have the plot on the steady state, this is a steady state, and try to choose a full cycle. Now we have complete 5 cycles. you have to right-click on the results and choose the Perform FFT report. Choose the last plot that you created and do the FFT report on, do the rectangular FFT on, for example, the magnitude of this. You will see the motor with healthy condition does not have any harmonics related to its main frequency, and it only has the 50 Hertz harmonic of the current. But the other motors, especially when you have more severe fault, you will have harmonics related to the main frequency. If I click on, for example, this frequency, you will see it's a harmonic related to the initial one. And it has some subharmonics smaller than the main one. And that's why we measure the current and its harmonic to diagnose. In many papers, you will see the FFT report will lead you to find the problem inside the motor. We will have a look on the results of the dynamic eccentricity 2, and we can start the question and answer session. I created a plot. It will take a little time, but if I zoom in the diagram, you will see these subharmonics are important too. You have to measure them and analyze them to be able to find the severity and type of the fault. In the dynamic eccentricity, we created FFT on the current. We learned how to do that, and we have the same problem in the induced voltage too. When you have healthy machine, the induced voltage will be pure sinusoidal waveform, and as you have the fault or mixed eccentricity or dynamic one, you will have some additional harmonics to the waveform. And you can do the same FFT procedure and workflow to find the frequency of these harmonics too. Thank you for joining this webinar. Now I'm glad to answer your questions in the chat box. Dimitri, can you help me with the questions, please?
Sure. Yeah. Thanks a lot, Ali. We will have some look into the chat. Just switching back to my screen sharing. Just give me a sec. So if any one of you guys, ladies, gentlemen, have some questions, feel free to raise them. I have received one question already that I will just read it now from the chat. Basically, it's regarding the validation of the simulation results, of the modeling results, and the experimental measurements. So basically, the question is regarding the fault severity levels, meaning like percentage of short-circuited windings or air gap eccentricity that correlates to a real case, to a real realistic scenario, let's say, that can be later on somehow related to experimental or measurement results. And what are the best practices, how to parameterize it, how to parameterize this sensitivity study using Maxwell ANSYS in order to be able to validate the modeling, the simulation results on the test bench or from the field, let's say from the real world, So how much, let's say, eccentricity would be realistic? Is it like more 30% or more 60%? Or if we are talking about the short circuit, like how many, let's say, turns you have short circuited in one string or in one binding or one phase in order to be able to simulate the real life scenario.
Yes, as I mentioned, in this case we talked about the eccentricity. Whatever is possible in the real life, we can simulate it in finite element softwares like ANSYS Maxwell too. For example, we have 1 millimeter air gap. If we move the air gap 0.3 millimeter, it is 30% eccentricity. What is realistic? All the values can be realistic. We can have healthy machine without any deformation or shift, or we can have 99% or 100% eccentricity, and it's the time that the rotor will touch the stator and the motor will burn out completely. So all the values are realistic, and that's why we modeled the fault with parameters to be able to model all of them. So the values all can be realistic. How to experiment the results and compare the results with experimental reports. Many papers work on this part. Many PhD theses worked on this part, and you will see different papers. About the other parts that I talked, because I'm sharing the screen, I didn't saw that I am out of the meeting. About the answer to the how much eccentricity is realistic, it depends on the machine. It's possible to have zero eccentricity as a healthy machine and 100% air gap eccentricity. That's the time that rotor will touch the stator and the winding will burn out and disaster will happen. So all the values between 0% and 100% is realistic. It depends on the motor that you are simulating. And that's why we created parametric simulation to have access to parametric sweep and changing the values. Many publications will validated the results with the real world machines. For example, they change the bearing sizes, will change the bearing balls to have dynamic eccentricity, and they validated the simulation results. If you create a complete and correct simulation and settings, you will be sure the finite element is the accurate the way of the simulation. So the results will be just like the reality if you create the simulation right with right settings. And about the parametric simulation and sensitivity analysis, as we created the parametric model, instead of going in Optimetris and adding parametric simulation, you can go and use the sensitivity analysis. But remember, the finite element simulation is very time-taking stuff, and if you model the sensitivity analysis or optimization within the finite element softwares, it will take a lot of time and the risk of not converging to the results. So in my project, I always use the parametric simulation near the specific point that I want to simulate. And you mentioned different type of faults like intern short circuit. Just like the eccentricity fault, if we have 10 number of turns inside each coil and we make them short circuited, for example 5 of them, we modeled 50% eccentricity for that coil, and or if we can divide it by the total number of turns, and we have that percentage of the fault. I have another course about this fault simulation inside ANSYS Maxwell in the WiredWhite website, and I think Dimitri shared a discount coupon for the whole courses of mine. You can have the discount coupon from the PowerPoint.
Right. Thanks a lot. The next one we have from Praneeth. It's in the chat. So this is regarding the symmetries. He's asking about that you mentioned that the symmetry is not possible for eccentricity analysis. So the question is, why can't we use the symmetry along the axial lengths?
We can have the symmetry around the axial lengths. When we have a 2D simulation, if I got the question right, when we have a 2D simulation, we have the uniform axial lengths. It is 2D. The part that I mentioned in the beginning of the presentation was when you create a model from RM expert, it will generate, for example, 90 degree of this motor, 1/4 of this motor, and just one magnet and 6 slots. And in these periodic boundaries, if you model eccentricity, it will do the uniform pattern. It will simulate the same pattern for all the other quarters too. That's why the results will be not accurate. I mentioned this point.
Oh, okay, right. Yeah. Hope that's clear now, Praneeth. If you have a follow-up question, just let us know in the chat. And I think we have the follow-up question regarding the short circuit fault. So
yes.
The question is how to introduce it in the model. So the approach is to segment the conductor and introduce different resistances to that, or how would you approach that, Ali? How to, let's say, introduce it in the modeling?
Yes, it depends on the scenario that you're modeling. For example, in this simulation, I have 2 coils inside each winding. The simplest scenario is we have 2 short circuit between these 2 coils. The whole coil, the whole number of turns, 10 conductors will be short circuited. In this way, you have to just remove these 2 coils from, for example, phase A and add them to another winding that is short circuited with different resistance and without any excitation, because it is short circuited. We don't have voltage excitation or current excitation. But this is the easiest scenario. If you have a percent of this winding, for example, it has 10 conductor in this coil, and you want to simulate 20%, just 2 conductors that are short circuited. In this scenario, you have to split this coil. The rest of the coil will remain, for example, in phase A, but this 20% will be short circuited, and you should assign different coils. There we have 8 number of turn coil and 2 number of turn coil. These 2 number will be connected to each other as a short circuit winding, and the rest will be connected to the phase of the initial phase that they were connected. It depends on your scenario, and I mentioned in the short circuit or intern short circuit videos in my course, I talked about it completely. You can have a view on the course content and have a better idea about the content and the videos.
Mm-hmm. All right, clear. Okay, makes sense. Thanks a lot, Ali. anyone else would like to raise a question? Otherwise, I will wrap this slowly up and go to the presentation again. So I would like also to mention that we have at least two of Ali's courses on our platform. You can check them online. They are on the courses page of our platform. So one is the induction motor simulation using ARM-Expert and ANSYS Maxwell. And another one is exactly on this fault analysis and fault modeling with FEM simulations and with Maxwell ANSYS. So it's worth checking if you guys, ladies, gentlemen, interested in that topic. And also, we would like to issue a discount code, a coupon code WiredWhite 10 for every attendee that was tuning in today. Please use it. Please feel free to take it with you and enjoy some other courses on the platform as well. So it's valid for the attendees. And also, we have a private tutoring also. So Ali is also one of our partners and platform members. So if you have any technical question, any technical issue in your project using Maxwell or using some fault analysis, let's say modeling use case, you can always ask for Ali's help to support with that. Yeah, and to wrap it up, I would like to thank you all for attending today. It was a very interesting topic since I'm also, I have been working on modeling in Maxwell a lot myself, so I found this topic very interesting myself. And very thankful to Ali for giving the speech today, for being a speaker today. And any final words from your side, Ali?
Thank you very much, and I'm very glad to have this webinar, to have opportunity to present this topic. It's a very interesting topic, and I hope it's very useful for the students and engineers too.
Yeah, absolutely. Perfect. Then, yeah, thanks a lot once again. Thank you all participants, attendees, and I hope you enjoyed it. And I'll see you, or we will see you, we will meet you in the next one very soon. Thank you so much and have a great evening. Bye-bye.
Thank you all. Bye-bye.